Welcome to a journey through the cosmos, where we'll explore the universe's most mysterious and powerful objects. What if I told you that scattered throughout space are invisible monsters so powerful they can trap light itself? And what if there might be cosmic shortcuts that could connect distant parts of the universe? Today, we're diving into the fascinating world of black holes and wormholes. We'll separate science fact from science fiction, discover how astronomers find invisible objects, and explore the theoretical bridges that could reshape our understanding of space and time. Get ready to see the universe through new eyes. Here's our roadmap to the cosmos. First, we'll tackle the fundamental question: what are black holes? We'll explore how gravity shapes space time and creates these cosmic giants. Next, in How We Find the Invisible, we'll discover the clever methods astronomers use to detect objects that emit no light, including recent groundbreaking discoveries. Then, we'll venture into pure theory with the wormhole hypothesis, exploring these theoretical bridges through space-time and why we haven't found one yet. Finally, in The Future of Discovery, we'll look ahead to what's next in cosmic exploration and how you can apply this knowledge. Ready to begin this cosmic adventure? Let's start with the force that governs everything in the universe: gravity. Imagine a bowling ball placed on a stretched trampoline. The ball creates a dip, and if you roll a marble nearby, it curves toward the ball. This is exactly how Einstein revolutionized our understanding of gravity. Massive objects like stars and planets don't just pull on things, they actually bend the fabric of spacetime itself. The more massive the object, the deeper the curve. This curved spacetime is what we experience as gravitational force. This simple but profound concept is the key to understanding how black holes work. So, what happens when you have an incredible amount of mass in a tiny space? This brings us to the birth of black holes. Picture a star 20 times more massive than our Sun. For millions of years, it burns bright, with nuclear fusion in its core fighting against its own crushing gravity. But eventually, the fuel runs out. Without the outward pressure from fusion, gravity wins. The star's core collapses in less than a second, creating a supernova explosion that can outshine an entire galaxy. But here's the incredible part: the remaining core, now compressed to unimaginable density, continues collapsing until it becomes a point of infinite density, a black hole. The space-time curvature becomes so extreme that nothing, not even light, can escape. Now that we know how a black hole is born, let's explore its most famous feature: the event horizon. Think of yourself in a river flowing toward a powerful waterfall. There's a point where, no matter how hard you swim upstream, the current is too strong. You're going over the falls. The event horizon works exactly like this invisible line in the river. It's not a physical surface you could touch, but rather a boundary in space around the black hole. Once anything crosses this boundary, the escape velocity needed to get out exceeds the speed of light. Since nothing can travel faster than light, nothing can escape, not matter, not energy, not even light itself. This is why we call them black holes. The event horizon is literally the point of no return. If the event horizon is the door, the singularity is the mysterious room it leads to. At the very center of every black hole lies what physicists call a singularity, a point where the star's entire mass has collapsed into zero volume, creating infinite density. It's here that our current understanding of physics completely breaks down. The equations that describe gravity and spacetime simply can't handle infinite values. We literally don't know what happens at a singularity. Is it truly a point of infinite density? Does space and time cease to exist there? These are some of the biggest unsolved mysteries in physics. What we do know is that the singularity represents the ultimate limit of our current scientific knowledge about the universe. We've learned what black holes are in theory: invisible objects with event horizons and singularities. But here's the fascinating challenge: how do you find something that emits no light in the vastness of space? It's like trying to find an invisible person in a crowded room. You can't see them directly, but you can observe their effects on everything around them. Astronomers have become cosmic detectives, developing ingenious methods to track down these hidden giants. They look for the telltale signs, the gravitational fingerprints that black holes leave on their cosmic neighborhoods. Let's explore how we've turned the impossible task of finding the invisible into one of astronomy's greatest success stories. The first clue is to watch the behavior of things we can see. Imagine watching a dancer spinning alone on stage, but something seems off about their movements. They're leaning and spinning as if partnered with someone invisible. That's exactly how astronomers discovered black holes. They observe stars that appear to be dancing with invisible partners. By measuring how fast these stars orbit and calculating the gravitational pull needed to keep them in that orbit, scientists can determine the mass of the unseen companion. When that mass exceeds about 3 times our sun's mass and emits no light, it must be a black hole. This method led to discovering Sagittarius A, the supermassive black hole at our galaxy's center, by watching stars rip around it at incredible speeds. It's not just stars they affect. Black holes bend the very path of light itself. Remember our trampoline analogy? When light from a distant star or galaxy passes near a black hole, it follows the curved spacetime, bending around the massive object like water flowing around a rock. This creates gravitational lensing, where the black hole acts like a cosmic magnifying glass. The result can be spectacular. We might see multiple images of the same distant galaxy, bright rings of light, or dramatically distorted shapes. Sometimes, a black hole perfectly aligns between us and a background object, creating what's called an Einstein ring, a perfect circle of light surrounding the dark silhouette of the black hole. This isn't just beautiful, it's direct confirmation of Einstein's theory about how gravity bends spacetime. These detection methods have led to amazing discoveries, even very recently. In 2024, astronomers discovered Gaia BH3, the most massive stellar black hole ever found in our galaxy, 33 times heavier than our Sun. It was detected by the Gaia Space Telescope, which noticed a star moving in a telltale orbital pattern around an invisible companion. Even more spectacular was 2019's breakthrough. The Event Horizon Telescope captured the first ever image of a black hole's shadow. By linking radio telescopes across the globe into one Earth-sized telescope, scientists photographed the bright ring of superheated gas surrounding the dark shadow of M87's, a supermassive black hole in a distant galaxy. This wasn't just a pretty picture, it was visual proof that black holes exist exactly as Einstein predicted. We've seen the strong evidence for black holes, from dancing stars to bent light to actual photographs. These cosmic giants are real, observed, and well understood. But now let's venture into the realm of pure theory and explore an even more mind-bending idea: wormholes. While black holes are science fact, wormholes remain science fiction, or at least science theory. They exist only in the equations of Einstein's general relativity, not in our telescopes. Yet the mathematics suggests something extraordinary: theoretical tunnels through space-time that could connect distant parts of the universe. Let's explore these fascinating but elusive cosmic shortcuts and understand why we haven't found one yet. Let's revisit our space-time fabric to understand this wild idea. Imagine you have a large piece of paper representing space-time. To travel from one corner to the opposite corner, you'd normally have to go across the entire surface, a very long journey. But what if you could fold the paper so the two corners touch, then punch a hole connecting them? Suddenly, you have a shortcut that bypasses the long surface route. This tunnel through the folded space is exactly what a wormhole would be: a bridge through space-time itself, also called an Einstein-Rosen bridge after the physicist who first described it mathematically. Instead of traveling the long way around through normal space, you could theoretically step through the wormhole and instantly emerge somewhere else in the universe. This sounds like the perfect way to explore the cosmos, but there's a major catch that keeps wormholes in the realm of theory. According to Einstein's equations, any wormhole that formed naturally would collapse faster than you could blink. We're talking about fractions of a second. To keep a wormhole open long enough for anything to pass through, you would need something called exotic matter, a hypothetical substance with negative energy density or negative mass. The problem? We have never observed exotic matter anywhere in the universe, and we don't even know if it can exist according to the laws of physics. Without this exotic matter to prop it open, a wormhole would snap shut like a rubber band, making it impossible to use as a cosmic highway. It's crucial not to confuse these two cosmic concepts. Let me make the distinction crystal clear. Black holes are real objects we've observed and photographed. They form when massive stars die, creating one-way passages to crushing gravitational fields. Once you cross the event horizon, there's no coming back. You're on a one-way trip to the singularity. Wormholes, on the other hand, are purely theoretical two-way bridges that exist only in equations. We've never found one, and they would require exotic matter we've never seen to stay open. Think of it this way. Black holes are the documented residents of our universe, while wormholes are the theoretical visitors that might be possible but have never shown up to the cosmic party. We've covered incredible ground on our cosmic journey, traveling from the real to the theoretical, from science fact to science possibility. We've explored how gravity bends spacetime, witnessed the birth of black holes from dying stars, learned how astronomers detect invisible objects through cosmic detective work, and distinguish between observed black holes and hypothetical wormholes. But the story of discovery is far from over. Science is always evolving, always asking new questions, always pushing the boundaries of what we know. So, what's the next chapter in this cosmic story? How will we learn more about these mysterious objects? And most importantly, how can you continue to be part of this incredible journey of discovery? Before we look to the future, let's recap the incredible ideas we've explored together. We discovered that gravity isn't just a pulling force, it's the curvature of space-time itself, like a bowling ball on a trampoline. We learned that black holes are born when massive stars collapse, creating regions where even light cannot escape past the event horizon. We saw how astronomers find these invisible giants by watching stars dance with unseen partners and observing how they bend light itself. We explored the theoretical possibility of wormholes as cosmic shortcuts, while understanding why they remain purely mathematical concepts requiring exotic matter we've never found. Most importantly, we learned to distinguish between scientific evidence and theoretical possibility, between what we know and what we imagine might be possible. This isn't just abstract knowledge sitting in your head. It's a new lens through which to see and understand the universe. Tonight, when you look up at the stars, you'll know that some of those points of light are dancing around invisible black holes. When you read about new space discoveries in the news, you'll understand the detective work behind finding invisible objects. You can follow the latest research from NASA, ESA, or the Event Horizon Telescope. Watch documentaries about cosmology with deeper appreciation. Share these cosmic mysteries with friends and family. Most importantly, carry forward that sense of wonder and curiosity. The same questions that brought you to this course: what's out there? How does it work? Are the driving force behind all scientific discovery. So, where do you go from here? Your journey into the cosmos is just beginning. The universe is an infinite library of mysteries waiting to be explored, and the same curiosity that brought you here is the engine that drives all scientific discovery. Every question you ask, every wonder you feel when looking at the night sky connects you to the greatest minds in history who dared to ask, "What's out there?" Keep asking questions. Keep looking up. Follow NASA's latest discoveries, explore PBS Spacetime for deeper dives, or visit your local planetarium. The universe has been waiting billions of years to be understood, and you're now part of that incredible story of discovery. Stay curious, stay amazed, and keep exploring the cosmic mysteries that surround us all.